Good morning everyone. Thank you for joining myself. I am Mr. Ish for these continuing videos on integral calculus. We have started the topic with Riemann sums and I have now presented several videos, perhaps more so than I had originally intended, but it's okay because the end result will be, by learning this technique and becoming more comfortable with it, the procedures of integral calculus will become more easy and satisfying for us. I have several, maybe you could say 2 more videos on Riemann sums coming up after this one. Maybe more, but I believe it'll be just 2. In this video I want to look at just the further examination, the Riemann sums technique, without too much of extra digression that I might be susceptible to doing, and getting right into it. Let's just start with a single question over here, and we can start with making some space. Imagine we have a circle over here, and we can give this an equation: x squared plus y squared is equal to 4. You know x squared plus y squared equals r squared represents the equation of a circle. Circles are not functions because they do not pass a vertical line test, but that's fine. We're just looking at the area of this circle, and you know here the radius will be equal to 2 because this right here, the 4 represents r squared. The root of that is just 2, so it represents the radius of 2. You know the Riemann technique, and this time let's opt for doing a number other than 4. We're trying to calculate, let's say, r8. So we know n is equal to 8. If we know n is equal to 8 and we know the radius is equal to 2, in all of these dimensions we know we have a minus 2 comma 0. Here we have a 2 comma 0. Here we'll have a 0 comma 2, and lastly here we'll have a 0 comma minus 2. These are our x and y intercepts. Once we have these intercepts and we're looking at things here along a horizontal reference line, you can say our x-axis. We know we have to look at the delta x, which is the interval of a Riemann rectangle. We could draw 8 Riemann rectangles, but I'll just draw, let's say, a few, assuming that they would cumulatively equal to 8, and we would be using the midpoint technique. I won't cluster this up with rectangles, but imagine we have 8 Riemann rectangles in here. The delta x would be b minus a, and we know what our interval will be. It'll be from minus 2 to 2. Our interval will be minus 2 to 2, so it's b minus a, the large number minus the smaller number, over n. So you'll have 1 over 2. 4 over 8 is 1 over 2, so 0.5. The next step we want to do, and you know you are comfortable with these techniques and procedures now, is our intervals. And then we'll have our sample points, which of course we'll always use and defer towards the midpoint, not the right endpoints, not the left endpoints, but the midpoints. And then we have some sort of function into which these midpoints values will feed into, and that'll give us our length. Remember this right here, the delta x indicates the width, the f of xi represents the length of each Riemann rectangle. If you're starting from minus 2 and we're going to 2, we know easily what our intervals will be. It will be minus 2 to minus 1.5 will be our first interval. The next interval will be minus 1.5 to minus 1, because we're going by halves. Then it will be minus 1 to minus 0.5, and then minus 0.5 to 0, and then 0 to 0.5, and then 0.5 to 1, 1 to 1.5, and we should have 8 of these spell out for us. 1.5 to 2 will be our last. You know these 4 and these 4, these being in the negative, these being in the positive, well, there'll be a symmetry which will develop around here in terms of the Riemann rectangles. These Riemann rectangles are symmetric because this circle is usually symmetric around, a perfectly drawn circle is symmetric around the x and the y axis. So whatever values you have, you'll have sharing of the values. The results which will be developing here will be shared, and you'll know what I'm talking about when you start seeing the values develop. Minus 2 to minus 1.5, well, we have to develop the middle of that. It'll be a minus 1.75, the midpoint. Minus 1.5 to minus 1 will be minus 1.25. Minus 1 to minus 0.5, it will be minus 0.75. From minus 0.5 to 0 it will be minus 0.25. Now you'll see the symmetry of values develop. From 0 to 0.5, of course, you have 0.25. Here you have 0.75. Here you have 1.25. The symmetry is here in terms of these values, and in terms of the results, ignoring the positive and the minus, you have 1.75. You see 1.75, 1.75, 1.25, 1.25. Ignore the positive and the minus. 0.75, 0.75, 0.25, 0.25. Well, you'll have symmetric results develop over here. But what's our function going to be? F of xi, what is it going to be? Well, we do have this equation over here, but this really cannot be that. You have to solve here in terms of y. y squared is equal to 4 minus x squared, therefore y is equal to root 4 minus x squared. But this root 4 minus x squared, by the presence of that radical, delimits this circle into a half circle, only looking at the top half. It eliminates this lower part of the circle because of the radical. You cannot feed in negative values, you end up having imaginary values. So what should our function be? Well, it could be radical 4 minus x squared, but since that defines only half a circle, maybe we can put a 2 before it because it fulfills the remainder of the circle. That multiplying by 2 will fill in for the lower part, which we are not. We're doubling in the top with the lower, and we have 2 root 4 minus x squared, so each of these values will feed in over there. Let's see what happens when we feed in and we start plugging in the values. We're going to feed in these individually. Well, we just have to do these 4, and these 4 will exactly be the same as their counterparts. I'll plug them in individually and see what we come up with. Each of these x values will come right into here, and we'll solve it out for over here. Here I get a 1.93, and I want to be here accurate with my numbers. 1.93649167, which should be the same as this because the minus and the positive is irrelevant in the presence of a square. Here I'll have a 1.93649167. Now let's do the 1.25. I get a 3.12249899, and then here it should be 3.12249899. Let's put in the 0.75 now. I get a 3.7 over here, 3.708099244, which should have the same corresponding value here with this 0.75, because here we have a symmetry going on. In terms of our results, in terms of our graph is symmetric about the x and the y axis, so you'll have these symmetric Riemann rectangles develop. Let's put the 0.25, 4 minus 0.25 square, you root it, multiply by 2, I get a 3.9, 68626,967, and then of course this value will be exactly the same. What will our area be for this circle over here? Let's come right over here. Area will be the cumulative sum of all of this multiplied by delta x, which you know right here to be a half. And let's do it. Let's add up all of these. We'll multiply it by this 0.5, and I'll plug the value right over here. When I add all of these, I get a cumulative sum of a 25.47143375, and I multiply by this 0.5 times 0.5, I get an area of 12.73571687, and I'm just going to recheck the answer, and I get this. We're not going to use an integration procedure here to verify this answer, but what we can do is use our basic equation. We know for a circle is pi r squared. We know radius here happens to be 2, so the area over here is a 4 pi, and we know there's a numerical value for pi. You can feed this into your calculator 4 times this 3.141 and onwards, as you know. Here I get a value from the calculator from using this 4 pi right over here. I get a computed result of this, and I'm going to plug the answer right here, 12.56637061, which you can take to be an accurate answer because it would be the same as you would get from an integration as you are getting from 4 pi, because pi r squared is a proven formula for the area of a circle. If you're plugging in the values and you're taking it to a good number of decimal places, it should be a good answer. And look over here, we have 12.73571687. Here we have 0.566. We differ a little bit from this point onward, which is fine. Look, we used a n value of 8. Had we used a larger number of n values or more rectangles or a more enhanced table of values over here, this value would have trimmed down towards this 12.566, and we would have a good answer, an accurate answer. Here we have a good answer. It's not true and accurate in terms of it being exactly as this, but it's not meant to be because the Riemann sum procedure is not accurate. It is a good approximation, especially when you're using these midpoint values. And that's all we were trying to do over here, was show you the exemplification of this technique for this specific presentation you have over here. Alright, let's look at this question. We're continuing with this examination of Riemann sum applications using interesting examples. We have y equals cosine x, and we have y equals half. I have not provided an interval over there, but we will shortly determine that interval. If we look at both of these functions, cosine x and half, and we are to equal them to each other, we can easily determine an interval bounded by 2 points of intersection. Cosine x is equal to half. And therefore x must equal to what? Inverse cosine of half. Let's do 0.5 inverse cosine, and we get a 60 degrees. 60 degrees. We know we have that to represent pi over 3, and we know cosine x is an even function. It has symmetry about the y-axis, and we can also say minus pi over 3. So we've suddenly determined that from a region of minus pi over 3 to positive pi over 3, minus 60 to 60, we can have a region, a narrow region of an infinite curve, because it goes from minus infinity to infinity. We can determine the area of the curve within that narrow region. If you are to graph it out, it won't be difficult because we are comfortable with graphing procedures. We know at minus 90 and positive 90, the cosine function has an x-intercept and it has a y-intercept at 0, 1, because cosine of 0 is equal to 1. You essentially have a part of a cosine wave coming down like that. But if you look at this y equals half, we know it's a horizontal line going across. So we're looking at this region of space between the two curves for which the area needs to be determined using Riemann applications. And now we know from this pi over 3 and minus pi over 3 that this point over here will be a minus pi over 3 or minus 60, and this point over here will be positive pi over 3 or positive 60. And we're looking at here things along a horizontal reference line such as the x-axis, or even y equals half is a horizontal reference line. Therefore we can do integration procedures using dx, and the equations must be presented in the y equals format, which they already are, cosine x and half. There's not much difficulty in this procedure at all, and I say let's calculate R4. We'll keep it up to an n value of 4, and we should determine what our interval will be. Delta x will be b minus a over n. B and a are pi over 3 and minus pi over 3. So pi over 3 minus pi over 3 is 2 pi over 3 over n, which is a 4. So what do you end up getting? 2 pi over 12, which is pi over 6. Each interval must be pi over 6, because you're going from 60, minus 60 to positive 60, going by 30s. And suddenly we have everything we need to get the process rolling. Interval will be by 30 degrees, starting from minus 60 up to positive 16. We should find midpoint values, as is always the norm, and then the f of xi, which needs to be determined, but it will not be hard. Our intervals will go from minus 60 to positive 60 by 30 degrees, so let's start doing it. Minus pi over 3 to minus pi over 6, and you'll have a bit of a symmetry come about here in terms of your values because of the even nature of this cosine function. And then minus pi over 6 to 0, and then 0 to pi over 6, and lastly pi over 6 to pi over 3. There's some quick rule which we haven't talked about, but we will in the near future. It has to do with the even nature of various functions, and especially when you're doing their integration procedures. And the rule goes something like this, and it serves as a shortcut. Anytime you're doing some sort of integration procedure, like from minus a to a for an even function, and you're doing the integration procedure f of x dx, which we will learn, and I guarantee you that we will. You can shorten it out such that you can bring a 2 in front and do from 0 to a f of x dx. What that really means, instead of looking from minus 60 to positive 60, we can essentially look from 0 to 60 and just look at this region of space right over here, from 0 to 60. But whatever the area is for this area right here, we would then double it, and it would fulfill the corresponding mirror symmetry portion on this other side. But that's what the rule is. Anytime you have minus a to a for an even function, you're looking at from 0 to a, that upper limit, but multiplying your result with a 2, because you have to double it. But we won't go too much into that because the video is about Riemann sums, and this is an advanced subject, well, relatively advanced, to come very shortly in a future video. Now we have to determine the midpoints. What's the midpoint of a minus 60 and a minus 30? Add them up. 60 plus 30 minus divided by 2, you get a minus pi over 4. And this is what I'm talking about, symmetry. Here you'll just have a positive pi over 4. Ignoring the signs, you have a 45 and a 45. Between a 30 and a 0 you'll have 15 degrees. Now how do we write 15 degrees in radian format? 12 or pi over 12, minus pi over 12 and positive pi over 12. So we've basically gotten our midpoint values that will feed into the function. Now what exactly is our function? Something we will learn again in a future video. Anytime you have a presentation such as this, up and down directed curves, you will always determine the extent of your rectangles or your function integration, because think about it, you have something which looks something like this, and you have this y-axis going, and you would be fitting in your 4 Riemann rectangles. I'm not drawing anything here to neatness, but you'd be essentially fitting in your 4 Riemann rectangles. Each of these rectangles basically has a height. What we're right now talking about is what's the extent of this height. Well, and normally how you would determine that is by looking at the top boundary curve, what the rectangle touches on the top, and you would minus from that what the rectangle touches on the bottom, which is what we will learn in the future. Now what is the top boundary of each of these rectangles? It's this cosine function. So the cosine function serves here as my top boundary curve. Here the y represents that the equation is in the y equals format. See, y equals cosine x, y equals half, hence the y. And the b here represents bottom. What's the bottom boundary curve for each of these Riemann rectangles if you were to draw them in this presentation here? Well, it would be your y equals half line, and that would be minus 1 over 2. So this right here, cosine x minus 1 over 2, represents the function into which each of these midpoint values will feed into. And that right there represents the length of each rectangle, or the extent or height of each rectangle. We're just creating space here for the eventual integration we'll do just to test our answer at the end. Well, we have everything we need now to finish it. We have our f of xi, cosine x minus half, which will represent the height of each rectangle, and we have to feed in these values. You can think of this as a 45 degrees, forget the minus positive, this is my 15 degrees. Here's 15, here's 45. So let's feed them in. Cosine of 45 minus half, I'll keep the calculator here on the degree mode. 45 cosine minus half, and I'm going to write out all the digits over here. 0.207106781. Likewise, this must be the same here too. Let's do cosine of 15 and run that through. Remember, cosine is an even function, so cosine of minus x is the same thing as cosine of x, the very nature of an even function. So if you can put 15 or minus 15 and you cosine it, you should still get the same. Let's do 15 cosine and we minus 0.5. The 0.5 is this minus half from this y equals half line. And we get over here 0.465925826. Likewise, this is the same over here. Now we should determine the area, and the area, as you know, is the cumulative sum of these lengths multiplied by your delta x. What was exactly our delta x? Did I write it out explicitly? It was 2 pi over 3 minus, I did write it out, but I remember I replaced it. 2 pi over 3, pi over 3 minus 2 pi over 3 was 2 pi over 3 divided by 4. I'm just rewriting it out here. It was 2 pi over 12, and it was pi over 6. Pi over 6 represented our delta x. So we'll do the cumulative sum of these lengths and we'll multiply by pi over 6, and we can do it numerically on a calculator. And let's do it. Area will be equal to what I've just said. I'll plug in the answer over here. When I do the cumulative lengths over here, I get 1.346065214 multiplied by pi over 6, which you can do on a calculator easily, and I get as this area of this region 0.704798097. So this here looks good. Now let's do the direct integration procedure, and I'll do that because I have not formally talked about those procedures yet, but let's do it. The direct integration would be, again, using that same technique that I was talking about, yt, your top boundary curve minus your lower boundary curve, and you would integrate from minus pi over 3 to pi over 3, because that's your interval, minus pi over 3 to positive pi over 3, or you can just do 0 to pi over 3 and multiply by 2, but we won't get into that fancy handiwork just yet. And it's the top boundary curve cosine x minus the lower boundary curve half, and with respect to dx. And let's plug in our answer. In the integration or the antiderivative or the integral procedure will lead you to have sine x. I was using terms over there we haven't learned yet, but we will. across pi over 3 and minus pi over 3. Let's be a little neat over here. Minus half will come as its antiderivative of x over 2. Again from pi over 3 to minus pi over 3. And let's plug in our final answer right over here using the direct integration procedure, which will represent an accurate area of this region. When I do this procedure over here and I do this numerical computation, I get this as the area calculated through the direct integration procedure, 0.6848532556. So you can see let's look at just the first three digits, 0.704 and 0.6884. We can see we're slightly off, but that's fine. We are expected to be slightly off when you're using the Riemann sum procedures, because you know already from the beginning it's not a true accurate representation of the area. It's an approximation only because you're using a bunch of assumptions. The biggest assumption being this, where you have a certain n value. Another assumption is whether you're using midpoint or right or left endpoints. All of these little minor inconsistencies add up during the procedure to give you a relatively good approximation, but not a true value of the area between the curves or the area below the curve. But that's fine. We're just learning a technique and I'm satisfied here with the outcome. We'll look at one more question right after this and then we'll be done with this video. So let's look over here at this next question. We have y squared equals minus x, which looks like a conic section parabola, a left-facing parabola. We have x equals minus 4, which you know is a vertical line, and then we have to calculate r4. If you think back to the equations of parabolas, conic sections, which you are familiar with, a conic section parabola, p-value of 1 over 4 will be a left-facing parabola with a vertex at the origin. It would have a focal point of minus 1 over 4 comma 0, but that's kind of irrelevant over here, but it could help us in terms of graphing. We're looking at something which looks something like this, a parabola which faces towards the left facing parabola. X equals minus 4, you can easily tell is a vertical line in going through minus 4 comma 0. But let's do something interesting over here. You see this x equals minus 4, we'll plug over here y squared is equal to minus 4. I'm just plugging this right in over here. So y squared is equal to 4 and y is equal to plus and minus 2. It will give us an indication of how these two curves combine together, and you would have something which comes right over here. This point right here would be minus 4 comma 2. This point right here would be minus 4 comma minus 2. Then you know this parabola would extend further out. I'm just not extending it further out just to keep it clean and neat, and we're looking basically at this area right there, the area of this, and we're not using integration over here, we're using the Riemann sum technique to calculate the area of this. I want to look at this in terms of a vertical reference line, you know, like a y-axis, but here x equals minus serves as a good reference line. There's nothing wrong with you using another vertical line in addition or other than your main axis. Instead of using y-axis, we can use this right here. X equals minus 4 can serve very well as a good vertical reference line. Let's redraw what we have over here to make it clean. We have something which looks like this, and here. If we were to draw Riemann rectangles horizontal, they would be looking like this. I'm not focusing here on the midpoint and the right and left hand points because I'm just showing a drawing over here. When always we're assuming that we're doing midpoints. Here I've drawn 1, 2, 3, 4, 5, 6, but I should have drawn only 4, but that's fine. You can mentally picture that there were 4 in here. We pluck out any of these rectangles and it would look like this. We would have a certain width over here and a certain length over here. Let's just do W and length. We know what our interval will be because we're looking at things here along a vertical reference line. If you remember, you have to present equations in the x equals format, no longer y equals but x equals. So you look at this y squared is equal to minus x, you solve for x. As a result of this procedure becomes x equals minus y squared. So that now becomes my new equation, minus y squared. And you know you would be doing integration normally with respect to dy, right? You're doing, remember, think back to the previous lessons I've talked about. Riemann sums, horizontally directed. We have to determine the extent of this because what we will end up doing is this table of values interval. Let's just use yi, our sample y value point, which would always be using the midpoints. As you know, we're not using left and right endpoints, we're always using midpoints, and then we could feed that value to a function and to get these cumulative lengths. What's our interval? Our interval is right here from -2 to +2, because when we're using vertical reference lines and we want to be looking at things along a vertical interval, like the previous question we were looking at things along a horizontal reference line, right, the x-axis, so therefore our interval was along the x-axis or x dimension. Here we're looking things, because of horizontal Riemann rectangles, we're looking at things on a vertical reference line, therefore we should be using a vertical lower limit and a vertical upper limit. Our interval -2 to 2, which is our b and a values, we should calculate our delta x, or let's just call delta y, would be b minus a over n. What's our upper limit? It's 2. What's our lower limit? -2 and over 4. 2 minus -2 is a 4, over 4 is 1. Our each interval is going to be 1. And our interval will be easy, going from -2 to 2, but by ones. Our first point will be from -2 to -1, then it will be -1 to 0, and then from 0 to 1, and then 1 to 2. The midpoints of these are easy. Midpoint of -2 and -1 is a -1.5. Midpoint of this is a -0.5. Again, we have symmetry here, but along in a y-axis dimension, this will become 0.5. And by symmetry, I mean symmetry of values. And here we'll have a positive 1.5. What's our function? This right here will be the hardest part to determine, is the function into which these values will feed into. The determination of function for those types of area questions, area between curves or area below curves, especially when you're using horizontal reference lines or horizontally directed Riemann rectangles, is usually more difficult than when you're using vertically oriented Riemann rectangles, because those are mentally more easier to grasp. Here we have to determine the extent. The extent over here, which has to be from a right and left direction. You see, from a right to left direction, you have to determine what the extent is. This extent represents the length. We know the left extent of all of these rectangles is this imaginary x equals -2. So we know we have a -2 over here as our leftmost extent. But the rightmost extent is anywhere along this curve, and this curve, as we've determined in terms of x, is a -y squared. -y squared. So what is our function? It's usually always from x right minus x left. And this is something you learn later on when we're looking at the formal area of curve videos. For these horizontally directed functions or equations or graphs or rectangles, you're always looking at things from an x right, xr. Don't worry about the terminology. We're always looking at things from the right to the left direction. So let me say that again. We're always looking at things in terms of determination of this extent from a right to a left direction. What's our right direction? It's -y squared. What's our left? It's a -2, but it's a -2, which becomes a +2. You see, our left equation here was x equals, actually why am I saying -2 as a -4? So here I'm making a silly mistake, -4, because it was x equals -4. So this right here will change. See, my bad, I was making a mistake. Again, rightmost extent is anywhere of these rectangles arising from the curve, which we've determined here to be -y squared. Hence, I have a -y squared. The leftmost extent of any of these rectangles is this x equals -4, which is right here -4, but the equation is right minus left. There's a minus here. That minus negates this minus and makes it a +4. So all of these values will feed into this formula right here, and then we'll plug in their numerical answers. These two will be the same, these two will be the same when you plug them in, because the square will negate the minuses. So now that we've determined that this is exactly what the function these values will feed into, so we have to run them through. Let's run these values through. We're going to run 1.5 and -1.5, 1.5 will lead the same values, -0.5, 0.5 will lead you to the same value, because this y square will negate the effect of these minuses. But it's more than that. We have a minus and compacting that, or compounding that. 1.5 minus square plus 4, I get a 1.75 over here. 1.75. Here I'll get a 1.75 as well. Let's put 0.5. 0.5 minus square it, and then you have to reattach a minus because there's a minus outside that y square, and then you plus 4 to it and you get 3.75. And this will likely be the same. And you know we have to now run this through the Riemann Sum Formula, which you know, limit as n approaches infinity, you can run it through this f of xi, cumulative sum of lengths times delta x. Here we can write f of yi and delta y, but let's just keep the terminology as is. Let's do the cumulative length and multiply by delta y, or your interval width. 1 here is meaningless. Whatever this thing ends up being is exactly what your area is. Let's add up all of those. I get an 11 over here as my area, 11. I want to just recheck to make sure the work is indeed right. These values here and then this. Let's recheck it and then confirm what we are doing is correct. And it looks good. Now let's just verify, or I can verify this using the integration procedure. This area over here, I know the area to be from a lower vertical limit along, see this -2 over here, to an upper vertical limit right here. And we're doing this formula xr minus xl, which you'll learn later on in a formalized manner. It'll be minus y squared plus 4 with regards to dy, because we are using here horizontally directed Riemann rectangles with a vertical reference line, so it has to be integration with respect to dy. When you integrate this, you get minus y cubed over 3 plus 4y with these upper and lower limits of -2 and 2. I will compute this for you and plug an answer, and we'll compare it to this 11. I get a -16 over 3 over here for this first part, and then over here I get plus 16. Place a decimal answer. 16 minus 16 divided by 3, I get a 10.66. Let's round it up to this. I get this as a computed representing. Now this time I won't say the actual true value, I'll say very close to the true value because I rounded it up. The true value is just 10.66, repeating to be the true area of this. But our Riemann calculated approximated value is 11, fairly close, and I'm confident that we are good over here. And again, we are happy that the Riemann technique is suitable to the point where when you're using the midpoint values, that you are confident that if you didn't know how to do direct integration procedures, you can rely on the Riemann technique to find areas between curves or areas under curves, and you can be relatively confident with your approximated calculated value. Because this here I would say is my true value, relatively true value due to the approximation, but this right here is my approximated value from the Riemann sum technique. And with that note, we will end this video because it was just a rehash and a reworking of questions using the Riemann sum technique for something which was slightly more out of the ordinary. I hope you enjoyed this video. Hopefully it bears fruit for you all. Remember, Riemann sum technique is an excellent technique, good to know because it's based in theory and it's very well suited for you to understand the integration procedures when you get into it. Thank you for watching. Have a nice day. Bye.